Okay, I think it's an honor for me to introduce Professor David Hankins. Uh, uh, Professor Hankins is currently a professor of logic at the University of Oxford and the Sir Peter Strawson Fellow at the University College Oxford. And, and he also has held many academic positions at universities or institutions all around the world. I remember in seeing 2011, Professor Hankins had given a talk at the National University of Singapore. Uh, when I was firstly attracted by his work on the Set-theoretic multiverse view. And after that, we have invited Professor Hankins to visit Shanghai in 2013, when he had given a series of talks, which was very successful, and we have some joint work since then. And I think, as many already knows, Professor Hankins is a very active researcher whose mainly works is in set theory. But also in many areas of logics, say even philosophical logic. He's also many work in other area of mathematics and also philosophy of mathematics or philosophy of some more general issues on infinity and truth. So today his talk is set-theoretic and arithmetic potentialism, the state of current developments. So let me give time to Professor Hankins.
Well, thank you very much. It's really a pleasure to be back in China and to see Ruji again and to speak to you all. And I would like to thank everyone for the welcoming comments in the chat. So thank you very much. It's really a pleasure to be here. Let me share my screen and then I can start my talk. Okay, so I'm hoping everyone can see that. Let me just adjust this here. Let's see. So, okay. Okay, so I want to talk about set-theoretic and arithmetic potentialism and tell you about what's been going on recently in this subject. So really the philosophical idea of potentialism, I think, goes all the way back, at least to Aristotle and the classical debate between actual and potential infinity. So of course, there are infinitely many natural numbers, but the question is, what sense of infinity is this? And the potentialist says, yes, the natural numbers are infinite, but this is a potential infinity. You can have more and more numbers, but you'll never have all of them. It will never be completed. Whereas the actualist says, yes, the natural numbers are infinite and they form an actually infinite set and a completed collection, and we can go on to use that completed collection to do more mathematics in further constructions. So recent work is really decoupling this potentialist idea from infinity. It's really about universe fragments. So the main idea of potentialism is that at any point in time or at any stage in the potentialist unfolding, we have only part of the universe, but you can have more. And so the potentialism idea is really about the relation of universe fragments to wholes, whether or not they are already infinite. So we define a potentialist system is simply any collection of structures in a common language with an accessibility relation on those structures, so that whenever one structure is accessing another or extending to another, then it should be because it's actually a substructure or it's embedding isomorphically to a substructure. So the domains of the universe fragments are growing as you follow the accessibility relation. And that's a Kripke model, and therefore we can define a modal semantics in that context. So for example, it's very natural to consider all graphs under graph extensions, or all groups, all fields, any kind of mathematical structure at all. So all models of a first order theory T, whatever your theory is. But of course, maybe the most philosophically interesting cases are these cases where we have the models of set theory considered under various natural extension concepts. So this is philosophically more connected with the idea of universe fragment and extending to larger universes. But also models of arithmetic maybe is even harking back to the classical idea about the natural numbers. Okay, so in any potentialist system, you get these notions of possibility and necessity. So a statement is possible, written with this diamond, if it's possible in M if there's some extension that satisfies phi. And it's necessary if all extensions have phi. So this is the modal interpretation. And in this way, we introduce the modal vocabulary into model theory. So it's very easy to verify some of these basic validities. So this is saying, if an implication holds in all extensions, then if the hypothesis holds in all extensions, then the conclusion holds in all extensions. But this is very easy to see. It's going to be true in any potentialist system. And similarly, if something is necessarily true, then it's necessary. That's just because we have insisted that the extension relation is reflexive. And this is reducing to transitivity. And so what this shows, the modal theory that you get is called S4. And so S4 is always valid in any potentialist system. Now, you can, because we're in a sort of quantifier realm here, we also get the converse Barkin formula. If it's necessarily true that every individual has a property, then every individual necessarily has the property. And that's just because of this requirement that the domains are inflationary. As you extend, then you never lose any individuals, you only add more, and that's what it takes to make this valid. So if we consider a potentialist system, then maybe it's convergent. Convergence means that if you're at a world and you go to two different ones, then there's a common extension of both of those. You know? And if you have a potentialist system that has that property, then then the axiom known as point 2 will be valid. If something is possibly necessary, then it's necessarily possible. Because you could have, if it's possibly necessary, then you could have gone somewhere where it's true in all extensions. But therefore, no matter where you could have gone elsewhere, you can always get back to one of those extensions precisely because of convergence. It's a very subtle thing, which is the difference between convergence and amalgamation. So amalgamation is when you have embeddings. Okay, you have a world and you embed it into two different worlds, and then you find a common extension such that the diagram commutes. It's stronger than just merely convergent because you insist that the way that you embed it is landing in the same place. And then you can validate point 2 with parameters. So if the potentialist system happens to be linearly ordered, then you're going to validate this axiom known as point 3, which says that if two things are possible, if phi and psi are both possible, then it's possible that one of them is true and the other one is still possible. So it's sort of like one of them happened first. You know, maybe you had phi first and psi was still to come, or maybe you had psi first and phi was still to come. So that's a validity if the potentialist system is linearly ordered. So the potentialist system remembers a bunch of models of a certain theory or something. Maybe it's a bunch of graphs or a bunch of groups or whatever, a bunch of models of set theory. And to be linearly ordered means the ones that you have in your potentialist system, any two of them are comparable by extension. So the maximality principle is the S5 axiom, and it says if a statement is possibly necessary, then it's already true. So anything that could become permanently true is already true, is what the maximality principle says. A way of thinking about it is that it's saying that you already went very high in the extension, so much so that anything that could have been made necessary is already true. Okay, so it's a very subtle principle to make it true. We can find models of this in various contexts. So I'll talk more about that. Okay, let's turn now to set-theoretic potentialism. So this is the view that the set-theoretic universe itself is never fully completed, but rather is unfolding gradually in some way. We never have the entire set-theoretic universe. We just have part of it. So for example, maybe you think that the set-theoretic universe is growing like a cumulative hierarchy, and at any moment we just have some part of it, some rank initial segment of it. But if we wait longer, then we get more. Okay, that would be rank initial segment potentialism. So rank potentialism, the universe fragments are the rank initial segments V alpha for the various ordinals. And as alpha increases, then you get bigger universe fragments. But there's other kinds of potentialism. For example, Grothendieck-Zermelo potentialism is the assertion that, well, usually we consider this if we have a lot of inaccessible cardinals, and we chop the universe off at various inaccessible cardinals, and those are all ZFC models, and each one of them can access the taller ones. So this is a very natural form of set-theoretic potentialism in a context when you expect there to be a lot of inaccessible cardinals. Now, there's also forcing potentialism, however. So this is not height potentialism, but sort of width potentialism. So you're in a universe of set theory, a model of set theory, and you can access the forcing extensions of that universe. So this is adding new subsets or new reals or new subsets of omega-1 or collapsing cardinals by forcing and so on. All of those things make a potentialist system consisting of a model and all of its forcing extensions. But then there's also sort of a kind of toy model version of set-theoretic potentialism, countable transitive model potentialism. We look at all of the countable transitive models of set theory, and each of them can maybe be extended in height by extending to a taller universe, and each of them maybe can be extended in width by forcing, say, or other width extensions, or you can do both. And so this forms a potentialist system. Now there's also top extensional potentialism. So this is a view, it's not the same as rank potentialism, because you don't insist that when you extend the set theoretic universe on top that you add all of the subsets. Maybe you just add some. And as, for example, appeared in my work with Ruji Yang, we considered models of set theory that had, say, different top extensions with different features and so on. And one can view this as a potentialist system. So one model of set theory is accessing the extensions that add new sets only on top at higher ranks. Then there's also end extensional potentialism. This is merely you have a model of set theory and you look at any extension of it that doesn't add new elements to old sets. So you can add new sets either on top or on the side, but you cannot add new elements to old sets. That's called an end extension. Okay, let's talk about arithmetic potentialism. So now the idea is we want to consider the models of arithmetic, so perhaps the models of piano arithmetic. So this is a very natural context. And we have all kinds of different natural extension concepts in models of arithmetic, just like we did for set theory. So maybe the most natural one is the end extension. So you have a model of arithmetic, possibly non-standard, and then you can extend it to a taller model of PA by adding new numbers, but only on top of the ones that you already have. So definitely models of PA can be related in that way. Or maybe you have arbitrary extension or cofinal extension and so on. There's all different kinds of extension concepts for the models of arithmetic. Okay, but I also mentioned this sort of more general context. For any first order theory, you can look at the submodel relation, and that makes a potentialist system. So maybe all graphs, or all groups, or all fields, or all orders of some kind, maybe all linear orders or all partial orders. And each collection forms a natural potentialist system. So let me just show you the power of the modal vocabulary, say, in the context of graphs. So we're going to do modal graph theory. So this is the potentialist system consisting of all graphs, and a graph thinks a statement is possible if there's a larger graph that thinks the statement is true. I claim that two-colorability is expressible. So if you have a graph G, To be two colorable means you can color the vertices, say red and blue, so that adjacent vertices get different colors. And this is not expressible in the language of graph theory, but it is expressible in modal graph theory, because you can say possibly there are two vertices so that every vertex is adjacent to exactly one of them, and adjacent vertices are adjacent to oppositely. So therefore, the two new vertices, sort of one of them points in effect at all the red ones, and one of them points at all the blue ones. So you can say possibly there are these points R and B that have this property, and that property is going to identify the coloring for you. So if there is a coloring, then you can add 2 points that fulfill the property. And if you can add 2 points that fulfill the property, then it gives you a coloring. So that's exactly two colorability. So this shows that the modal vocabulary is strictly stronger than just ordinary graph theory. So for example, connectivity is also expressible. So if you have a graph and you have two vertices, say X and Y, and you want to express that X is connected to Y, so that means that there's a finite path that goes from X to Y. So we can follow these edges to get from X to Y. So they're connected. I want to express that in modal graph theory by saying, necessarily, if I have a vertex that's adjacent to X and whose neighbors are closed under adjacency, then it's connected to Y. So this is saying necessarily if C is adjacent to X and any neighbors of C, if C is adjacent to U and V is adjacent to U, but not C, then C is adjacent to V. So that's saying it's closed under adjacency. So the things that are adjacent to C, I can follow. And so then I'll be adjacent to Y. So if X is connected to Y, then clearly it's going to have this property. And if it isn't, then I can put a point C that's adjacent just to the component of X. And it will be closed under adjacency, but it won't be adjacent to Y. And so therefore connectivity is expressible. Now we've explored this much further. And in fact, there's huge parts of set theory that are interpretable in modal graph theory. So it's somehow extremely strong in terms of its expressive and interpretive capacity. But there's open questions about modal graph theory, exactly what the power is. So what is the goal? Well, we want to look at the modal commitments of these various potentialist perspectives in all these different potentialist conceptions, especially in set theory and arithmetic, and to look at the various natural ones. And we want to find the new potentialist axioms or principles expressed in that modal language and discover the power of that potentialist language. So let's just look at a few more validities. So here's an axiom. It says, if something is necessarily possible, then it's possibly necessary. So the question is this valid for forcing potentialism? And the answer is no, because the continuum hypothesis is true, is necessarily possible for forcing potentialism, because over any model of set theory, you can always force the continuum hypothesis. So therefore, it's necessary that it's possible. But it's not possibly necessary because also over any model of set theory, you can force the negation of the continuum hypothesis. You can turn it on and off and on and off. And that violates this axiom. Okay, well, is it valid for graph theory? So if you have a statement that's necessarily possible, then is it possibly necessary? And maybe it's fun to think about this. So in graphs, the question is this valid or not? And the answer is no, because it's necessarily possible that the diameter is 2. Because if I have any graph, then I can add a vertex that's connected to everybody. And now the diameter will be 2, meaning that any 2 points have a path of length 2, connecting them. But it's not possibly necessary that the diameter is 2, because you can also destroy that property. Every graph, I can just add 17 isolated points, and now the diameter won't be 2 anymore. Okay, so here's another example. if something is possibly necessary, then if it's true, then it's necessary. Is that valid? These are all sort of standard modal axioms. If you open a book in modal logic, you'll find dozens, hundreds of these kind of axioms. And so one can just look at whether they're valid for your potentialist system or not. So is it valid, say, in fields? If we consider all fields under field extensions, So if something is possibly necessary, then if it's true, does that mean that it's necessarily true? So you can make it permanent. That's what this says. Possibly necessary means you can go to a field where it's true in all extensions. All right. And it is true. So does that mean that you already made it permanent or not? Did you make it necessary? And the answer is no. Because, for example, it's possibly necessary, this disjunction, or, my statement has two parts. Either the cube root of 2 exists, or there's some number with no square root. So I can make this true because I can always add this root. I mean, if I'm talking about, I guess, fields of characteristic 0, say. So I can always go to a field extension where I've added this object. And then it would be necessarily true because I'm having the first part of the OR. So therefore, it's necessarily true. But I could also make this statement true, not by adding that root, but by adding a transcendental element. And that wouldn't have a square root. Therefore, it could be true, but not necessarily true, because if I add the transcendental element, then I could go to the algebraic closure, or I could close under square roots, under all square roots, but it wouldn't add the cube root because 2 and 3 are relatively prime. Okay, what about, is it valid for growth empty Zermelo potentialism? This is the one where you chop off the set-theoretic universe at inaccessible cardinals. And it's not, because if you look at the statement, either there are an even number of inaccessible cardinals or infinitely many. So you can make that necessarily true by just going above the first omega many inaccessible cardinals. Then you've made the second part of it necessary, and so it's possibly necessary. But before you did that, maybe you just went up above the fifth inaccessible or above the sixth one. So you made it an even finite number, but then you made it true, but it wasn't necessarily true, because if you go one more, it won't be true anymore. So you can turn it on and off, on and off, on and off, and then you can make it permanently on after. And that's what it takes to violate this principle. Okay, so here's another one. Well, this is the point 3 axiom, the linearity. So the linearity axiom, if two things are possible, then it's possible that one of them happened and the other one is still to come. Is that valid for forcing potentialism? So the answer is not in all models. And for example, in the constructible universe, you can partition omega 1 into disjoint stationary sets, and by forcing, you can shoot a club through one of them or through the other, and you can express, look, this one is stationary, but that one isn't, or the other statement is the other set is stationary, but the first one isn't, and so on. So there's two ways to do it, and you can express that you did one of them but not the other one, and then the point is that once you do one of those, then the other one isn't possible anymore. And so both of them are possible, but both of these are impossible, and that violates point 3. It's a lack of linearity in the forcing extensions. One of them came first. I'm sorry, they're sort of incomparable. It's a branching point. It's violating the linearity principle. Okay, is it valid for the countable models of ZFC? This was a shocking result for me. I was really surprised to learn this. But it's a consequence. I mean, the theorem was very surprising to me. Any two countable models of ZFC are comparable by embeddability. One of them is isomorphic to a submodel of the other. And therefore, that's a linearity principle which validates point 3. So it's really quite surprising. Okay, let's now move on to the next section here. So we can often easily observe that a certain theory is valid, and like if it's convergent or amalgamation, or if it's linearly ordered, we can get these theories are valid. That's usually easy. But it's more difficult to prove upper bounds, to prove that something isn't valid. So far, we just went through a half a dozen examples, but those were all kind of ad hoc arguments. We didn't have a method. We just said, well, in this validity is not valid for graphs, or this validity is not valid for fields. And we did it by kind of tricks, each case separately. And so what we really want are more robust tools for analyzing what are the validities of a model. And that's what I want to tell you about. We have some tools to do that. So we can establish upper bounds on the validities by using the control statement method. And the control statements are these sort of whimsical names that we've given to them. Switches and dials and buttons and ratchets and rail yards. And so I'd like to tell you about how these control statements work. So this way of thinking really started with my work with Benedict Loewe on the modal logic of forcing. So a switch is a statement so that you can turn it on and off as you follow accessibility. So like a light switch, you can turn it on and off as much as you want. So possibly S and possibly not S are true at every world. So that means given any model, given any world in the potentialist system, you can make it true and then false and true and false again as much as you want. If you have many switches, then they are independent. If you can make any pattern happen by going to a bigger one, you want the first three, you want the pattern to be true, true, false, and then true, false, true, and then true, true, false again, and then false, false, false. Whatever pattern you want, you can always get that pattern. So, for example, in forcing potentialism, where you have a model of set theory and you look at its forcing extensions, we already observed that the continuum hypothesis is a switch, because you can force it to be true, and then force it to be false, and force it to be true, force it to be false again. And a similar idea, if you control the generalized continuum hypothesis, say at the Aleph n cardinals, you can make whatever finite pattern you want in the GCH pattern, and therefore those switches are independent. Well, what about graph potentialism? So we look at all graphs, and I want switches. So the existence of an isolated point is a switch, because whatever graph you have, I can add an isolated point. But then I can add a point connected to everybody that's going to destroy all the isolated points. And then I can add an isolated point and then destroy. And so I can make it true or false as much as I want. And if I say Sn is that there is an isolated n cycle, so maybe I have a triangle or a square, a 4-point cycle, a 5 cycle, that's not connected to anything else. So those switches are independent, because I can make a triangle and a pentagon, and then I can destroy all of them by adding a point that's connected to everybody. And then I can create a new pattern of truth values for these. So they're independent. Now, what about in field potentialism? So I can add a field element with no square root. I can add a transcendental element. It won't have a square root. But then I can go to the algebraic closure, and I've added all the square roots. So I can turn it on and off and on and off. Or I can make independent switches. So I can, the existence of an element without a pth root for a prime p. So not just square root, but cube root or fifth root, seventh root, and so on. And those can be controlled independently of each other. So the main reason to care about switches is that if you have switches, if you have arbitrarily large finite families of switches, independent switches, then the validities are contained within S5. So this is the upper bound. Existence of switches implies that the validities will be contained in the modal theory S5. Okay. So now what is a dial? A dial is a sequence of switches, a possibly finite sequence or possibly infinite, such that every world satisfies exactly one, and all of them is possible. So the way I think about it is, it's a dial, and you can set the dial number to have whatever value you want. You want the dial value to be 2, you can make D2 true and none of the other ones. You want the dial value to be 17, you can make D17 true just by going to an extension. Now, existence of dials turns out to be equivalent to existence of independent switches. So they're actually equivalent. If you just think about the binary bits of the dial values, those are going to be switches, independent switches. Okay, so let's make some dials in graphs, say. Well, let Dn assert there are n isolated points. I can have whatever number of isolated points I want. I could add 1 or 2 or 3 and so on, or I can kill all of them, 0. So however many you want, you can have exactly that many. And so those are dials. What about dials in forcing potentialism? So we could say the continuum, so the cardinality of the reals can be whatever Aleph n you want. You can force to make the size of the reals whatever Aleph n you would like. What about in groups? We consider all groups under the subgroup relation. You know, what's a dial? So, well, we can assert that the center has size n. So first of all, every group is extended to a group that has no center by going to the permutation group. And then we can take a direct sum with a group of size n, within a abelian group of size n. And so then the center will have size n. Okay, let's go to the next kind of control statement, a button. A button is a statement that's possibly necessary. So the idea is, it's different from a switch. A switch, you can turn it on and off. A button, you can push it, but then you're done. It's necessary. You can't unpush it. You know? So it's pushed when necessary be, and otherwise it's unpushed, not yet pushed. A family of buttons and switches is independent. That means that you can control them independently so you can push any button you want without pushing the other ones, and you can set the switches without inadvertently pushing some buttons. Well, let's make buttons in graphs. So we have graph potentialism, and I want to make a possibly necessary statement. So, for example, the existence of a triangle. Maybe the graph doesn't yet have a triangle, but I could put one in. I can extend the graph so that there's a triangle. And then that would be necessary then. Or, for example, the existence of various finite graphs. Maybe I have a triangle, but I don't yet have a 4-cycle or a 5-cycle. So those can be controlled independently, because whatever, if I want to add a 7-cycle, I can do so without adding a triangle. And once I have one of those things, then it's going to be still there in any further extension. So it's possibly necessary. So there's buttons in groups, in the space of all groups. To make the group non-abelian is a button, because once you add a non-commuting element, then it won't ever be abelian again as you make a bigger group. You know, so that's a button. Or you can, to create a copy of certain finite subgroups. If you have a certain finite subgroup, then it's still going to be that finite subgroup is still going to be there as you make the group bigger. So what about buttons in forcing potentialism? So, well, to collapse the omega-1 of the constructible universe is a button, because you can force to make that cardinal collapse to make it countable in a forcing extension. And once you do that, it will still be countable in all further forcing extensions. or for example, to shoot clubs through various definable sets. These are independent buttons. If I partition omega 1 into definable stationary sets, I can shoot clubs through any one of them that I want, and it won't destroy any of the other ones. So what about buttons in arithmetic and extensional potentialism? So here we have the models of piano arithmetic under end extension, and I want to have buttons there. So the assertion I claim not con PA is a button, because once you have a model of PA that thinks not con PA, then any end extension will also still have that proof of a contradiction, and therefore it's still going to be true in any further extension. But if con PA holds, so the question is it a button? So once it's true, it stays true, but if it's not yet true, then you can make it true, because if con PA holds, then this theory is consistent by the incompleteness theorem, and therefore inside the model we can make the Henkin theory of this theory, and therefore the corresponding Henkin model will be an end extension because it's definable inside the model, and the model knows that it's an initial segment of any model that it can build. And so therefore, if you don't have not con PA yet, then there's an end extension where you do have it. So the main point of buttons is that if you have a potentialist system that has independent buttons and switches, then the validities will be contained within S4.2. So this again is an upper bound. This theorem is the tool. It's showing how to find the upper bound on the validities. You have to identify buttons and switches, independent buttons and switches, and then you'll know that you can't have something valid outside of S4.2. Okay, well, what is a ratchet? Maybe people aren't necessarily familiar with this word. In English, a ratchet is a certain tool. It's like a wrench, but it only goes one way. You turn it and then click, 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 and then you turn it again, and it just is for tightening. That's a ratchet. I have no idea what the Chinese word, maybe someone can say what the Chinese word is, because I'm not sure if it's understood. Does anyone know what the Chinese word for a ratchet is? No, so it's a tool. It's for tightening a nut, but it only where you tighten it and then it slips back. Click, 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 and then tighten it. Click, 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 click. So it's a tool, like a mechanic would use it. Okay, so is it okay? All right. So it's in my, this is a metaphor. In my context, a ratchet is a sequence of buttons so that each of them implies the earlier one, and the next one can be pushed without pushing the previous one. So it only goes up. It's a unidirectional sequence. You can make it more and more and more of them true, but once you make one true, all the previous ones are automatically true. So it's one-way operation. Okay. So what is a ratchet in CCC forcing potentialism? For example, let Rn assert that the continuum is at least Aleph n. With CCC forcing, you don't collapse cardinals, but you can add as many reals as you want. You can make it bigger and bigger and bigger. It only is going to get bigger. So you can make it exactly as big as you want without necessarily making it bigger than that. So this is achieving the ratchet property. What about graph theory? Well, let Rn assert that there's a complete subgraph with n vertices. So if you have a complete subgraph with 5, then you also have one with 4 and 3 and so on. So but maybe you don't have one with 6 yet, but you could add more vertices and make one with 6. You can make it as big as you want without making the next one true necessarily. Okay, this is a weak form. This is like semi-independence. They're buttons, but they're not completely independent because each one implies the previous one. Okay, the point of ratchets is that if you have ratchets, then the validities are contained within S4.3. So in each case, the control statements give us a bound on the validities. And this is the main point. Okay, so here's a railway switch. So you're standing by the railway tracks and there's a switch, a branch, and you can make the train is coming. You can make it go left or you can make it go right, you know. But once the train passes, it's all done. So possibly necessary R and possibly necessary not R. So the train went one way or the train went the other way, but once it's gone, then it's necessary, whatever you chose. Yeah, that's a railway switch. Okay. So so once you make it necessary, that's like the train is passed. It went left or it went right. I should have said right and left because it's R, I guess. Okay. This contradicts S4.2. If you have such a thing, it's because this was the convergence axiom, remember? So convergence, S4.2 says if two things are possible, then you can go, if two things are possibly necessary, then they're necessarily possible. But that's exactly contradicting this, right? Because once you made necessary R, this one isn't possible anymore. And once you did this one, the other one isn't possible. So you can't have S4.2 if you have a railway switch. Yeah. Now, the Rosser sentence is a railway switch in arithmetic. So the Rosser sentence, this is the self-referential sentence, rho. It says, for any proof of rho, there's a shorter proof of not rho. You use this to prove the incompleteness theorem, the Gödel-Rosser version of the incompleteness theorem. Now, so in order to tell which one was true, rho or not rho, the question is who has the smaller proof? Did the Rosser sentence have the smaller proof, or did the negation have the smaller proof? You know, so if you have con PA, then you can extend it to make either one of those true, because the Rosser sentence is independent of PA if PA is consistent. But once you make one of them true, then it's necessary in any further end extension, the smallest proof won't change. And therefore the Rosser sentence is a railway switch, because you can make rho have the smallest proof or not rho, and that's going to affect the truth of these in a way that's going to be necessary by all further end extensions. So that shows that S4.2 is not valid in arithmetic potentialism because we have a railway switch. Okay, so a rail yard, before that was just one switch, but a rail yard has a lot of switches. Yeah, it's an assemblage of switches. It's like a finite pre-tree. And the rail yard has each node in the tree is associated with a statement, so that possibility in the tree is, reachability in the tree is the same as possibility of those statements. Okay, this is maybe a bit detailed, but the main idea is that the possibility in the potentialist system matches the reachability in that finite tree. Okay, now this is the use of the control statement method. If you have rail yards for every finite pre-tree, then the modal validities are exactly S4. That's as little as it can be. S4 is always valid. And so if it's contained in S4, then it's equal to S4. Okay, so the existence of rail yard labelings tells you exactly what the validities of your potentialist system are. Okay, so, right, so this is a kind of summary. Let me just go all the way down. If you have switches, then it's contained in S5. If you have buttons and switches, it's contained in S4.2. If you have switches and a ratchet, then it's contained in S4.3. And if you have rail yards, then it's identical to S4. So this is the power of the control statement method. And the main advantage is that you can identify often these control statements without knowing anything about modal logic. So set theorists can find their validities using only set theory, basically. And model theorists, you only need to know graph theory in order to figure out if there are buttons and switches and so on. It's very natural to think about those statements in graph theory only. And so because of that, because of those theorems, we can then, inside the subject itself, prove the validities about the potentialist system we're interested in. Okay, so let me go to the last section now. I hope I have time. Which is connected with the universal finite sequence. Okay, so this is we have the universal algorithm in models of arithmetic, and there's related versions of it in set-theoretic rank potentialism and end-extensional potentialism. So we're going to consider the models of arithmetic as a potentialist system. We look at models of PA under end-extension relation. Then the theorem is that the potentialist validities of the models of PA are exactly S4. Yeah. And if we allow, if we allow parameters, it's exactly S4. If we're just looking at sentences, then it's something between S4 and S5, and those bounds are sharp. You cannot, we have examples realizing. The hard part is really the S4 part, and this comes from finding rail yards. We need to find rail yards, and this is a consequence of the universal algorithm. So this is an absolutely beautiful theorem due to Hugh Woodin, and what he proved is that there's a Turing machine program that enumerates a finite sequence, and PA proves that. So it's gonna, the program spits out finitely many numbers on the tape. It keeps running, but it's only going to give you finitely many numbers. And in the standard model, it doesn't actually give you anything, you know, but it has this extension property. Given any model of PA, if it's giving you some sequence S there, maybe empty, then for any extension of S to T, then there's some end extension of the model in which the program, the very same program, gives you that extension. So it's a program that can do whatever you want if you run it in the right universe. It can give you whatever numbers you want. You say, well, it's given me some sequence. I really wish the next number was 17. Then there's some end extension where the next number is 17. And then you say, well, now I want a 34. Then you can, there's another extension where the next number after that is 34, and so on. You can make it do whatever you want. Okay, and that leads to this sort of branching possibility. You had a model M, you can find an extension in which the sequence, in which the next number was 17, or you could have made it 16. And then once you do that, now those two models can't be brought together again, because one of them thought the next number was 17 and one of them thought the next number was 16. And then once you do that, then there's further branching. And so we get this kind of tree structure for the models of arithmetic. And then we can use that universal algorithm to label any finite pre-tree. So this is a rail yard, and we can use the numbers on the universal sequence, interpret those numbers as a way of climbing through this tree, so we can thereby get a rail yard labeling for any finite pre-tree, and that's why the modal logic is exactly S4. Now let me just mention the set-theoretic analog. So when I learned Woodin's theorem about arithmetic, I thought, well, there should be a set theory version of this theorem. And so Woodin and I together proved that if you have top extensional potentialism, so this is where we have the models of set theory and we're allowed to top extend them, then we also have a universal algorithm. There's a sigma 2 definable finite sequence, so in set theory, and ZFC proves that it's finite. And it has the universal extension property. So given any model of set theory, any countable model of set theory in which it's a certain sequence, then for any desired extension of that sequence, there's a top extension of the model in which the sequence is exactly that extension. And from that, it follows that the top extensional potentialism is giving you exactly S4. It validates exactly S4. There's no other principles valid there. Now, also with end extensional potentialism, Cameron Williams and I did an analogous thing. It won't be a sigma 2 definition, but a sigma 1 definition there. So we have a sigma 1 definable finite sequence. ZFC proves that it's finite, and it has that extension property given any countable model of set theory in which the sequence is S, then given any finite extension of that sequence, little t, there's some end extension where the sequence is exactly t. And that gives you railway switches and rail yard labelings. And so the modal validities are contained exactly in S4, and so therefore equal to S4. Okay, that's it. That's all I had to say. So thank you very much. It was really a pleasure to be here. So let me stop this share. I'm happy to have questions.
Okay, thank you, Professor Hankins. So this is the talk, the last talk today, I think. Do you have comments or questions?
Oh, I see. There's a question in the chat I see here. Let's see. So someone's asking if there's any difference between countable transitive model forcing potentialism and multiverse view of set theoretic universes. Yeah, so this is a very interesting question. So when, I mean, there's sort of, philosophically, there's sort of two ways to look at the multiverse view. If we think about the actual multiverse, it's about the multiverse of the full set theoretic universe and maybe classes and taller universes and so on. And this is difficult for us to get knowledge about, because how could we ever find those other universes or go there, right? And so meanwhile, in ZFC, though, we can study the countable, say the countable transitive models or the countable models of set theory as a kind of toy multiverse. And we can prove a lot of theorems about the nature of those, of the toy multiverse. And maybe there's a kind of philosophical program of, if you can prove something is true of the toy multiverse, then you use that as a way of learning about maybe what the nature of the actual multiverse is like, right? So this is the program that people are following. And so this is a reason why maybe to think that, well, it follows from a theorem of Barwise that every model, every countable model of ZFC has an end extension to a model of V equal L. It's rather surprising, but it's true. It has to be taller. I mean, it will have more ordinals, but maybe that's a reason to think that the actual set theoretic universe, even when we have supercompact cardinals or wooden cardinals or whatever, maybe there's an extension in which V equal L again. You know, so if we took Barwise's theorem as suggesting that, it might lead you to look a little differently on the V equal L axiom from the multiverse perspective. Okay, I'm not sure if that answered the question, but so I view that countable case as a mathematical undertaking, and it has relevance for the philosophical understanding of what you might think of as the full multiverse. Okay, let's see. There's more questions here. Someone asked, how do you define shorter? And I'm not sure what the context was for that. So we were talking about models of set theory, and the height is maybe measured by the ordinals. So we have taller ones and shorter ones. Or models of arithmetic, maybe, of course, also can be considered in terms of their height. And so if I use the word shorter, I think I was probably talking about that. Let's see, someone else said,
it's a conflict with potentialism. I mean, someone asked if the potentialism is a conflict with potentialism.
Right. So, okay, if you, when you say Platonism, maybe traditionally part of what people meant by Platonism in set theory was combined with universalism. I mean, I think that the views were conflated maybe for decades, that when someone said, I'm a Platonist in set theory, then it used to be understood that they're asserting that there's only one set theoretic universe. But really Platonism should be about the realism, about the real existence of the set theoretic objects. And so it's not in conflict with a multiverse perspective, right? So if you think that maybe there's many different universes, many different set theoretic concepts, each giving rise to their own universe, and maybe they're all fully real, And so this is a Platonist view, but it's not a universe view, right? So we can have real existence. And one can look at potentialism as helping us to express the kinds of relations that we might expect in a multiverse view. If you think there's a lot of different set-theoretic universes, then you want to understand how are they related. And maybe you have a kind of modal idea about how those set-theoretic universes are related. And so then it becomes a kind of potentialism. And so one would want to know, well, which modal principles are you committed to in your kind of potentialism? If you have a view that the set-theoretic universe has a potential character and it's just growing linearly, like with the V alphas, then you're going to be committed to S4.3 because they're linearly ordered. But there's another way of sort of criticizing that view is not actually potentialist. If the universe is growing and it's inevitable how the sets come in because we just have to wait longer, then there's a kind of implicit actualism in that view. Whereas the branching case is a much more radical kind of potentialism. So if you have the view of, if you're a potentialist, say about arithmetic even, you only have some of the numbers at a time and more are coming in. Then if you have a view that there's linear inevitability about the nature of the numbers that come in, then that's a kind of implicit actualism, isn't it? Because you think, well, you don't have all of them, but what's going to happen is somehow determined, and there won't be choices to be made. Whereas if you have this kind of branching kind of potentialism, like maybe the Rosser sentence is going to turn out to be true, or the negation, and you don't know which one, but once that happens, then you're stuck with it, right? Then that's a much more radically potentialist view. So I think that the introduction of this modal view into potentialism is clarifying issues that maybe should be talked about the nature of potentialism. So I guess that's also part of my view.
Hi, Joel.
Sure.
Thanks for the talk. I have a question.
Sure, please.
Do you think there's anything substantial to be done in considering a bimodal potentialist system? Now, the intuition here is you not only consider a potential future, you also consider sort of your potential past, so to speak. Namely, I mean, there are a few notions that come to mind in the models or ground models, right? Or
yes.
Elements in the universe that are models, or like symmetric extensions, so on and so forth. Now, I would think that for ground models, this will be kind of straightforward by the ground model definability theorem, right? You just take the inverses of the forcing extension. But what about other notions? Do you think there's something interesting to be said there?
Yes, absolutely. So Benedict Lowe and I have a paper exactly about that question. And it's called Moving Up and Down in the Multiverse or something. And so we provide examples of models where you have upward S4.2 and downward S4.2 or downward S5 and so on. And so we make some examples of exactly the kind that you're asking about. But I think there's a lot of open questions, a huge amount of work still to be done in this area. And so right now, currently, Victoria Gitman and I are trying to prove a downward version of the universal algorithm. So the universal algorithm says, where there's this Turing machine program that enumerates a finite sequence in models of arithmetic, and you can make the next number whatever you want by going to an end extension. What we want to prove is that given any non-standard model in which the sequence is something, then can you find a cut, an initial segment of the model in which the sequence had done only that much so far? And we don't know the answer to this yet, but I find it very much connected with your question, so this bimodal case. So I think it's extremely natural question. And there's really a lot of open questions about it. So I think it's very interesting.
Okay, thank you.
Yes. I wish I had more to say about it, but I'm trying to figure it out. So please help us out, maybe.
Okay, do we have more questions or comments? Since it's the last talk, we have more time to do that. But okay, if there's no more questions, thanks to Professor Hankins for the very exciting talk. Okay.
Thank you very much.
Thank you.
It was a pleasure to be here.
Shall we have a group photo? Where people in Beijing venue, Tianjin venue, me in Shanghai, and people from maybe from United States. So shall we show up all?
得改变，换成那种模式。对，所有人都打开，不是这样，所有人都打开，然后。
OK。
可以。
OK。
还不如截屏啊。
打开截屏。
对，都打开，然后截屏。
下面就打开了。
截屏吗？是随截。
可以啊，这受不了。
你打后面这个打，对，你打开一个。你看这字是什么？钥匙拿起来。
谁做个截屏？
我这边好，我这里做。
还很多事情都没打开呢。
对，
还有more。
很多人没打开呢。
事情都打开，把它
往那边走，这个往这边是吗？还有和你再往这边走。这个可以有这么不行吗？